Now we really want to start talking about transformations. But to understand the idea of a transformation, let's go back to Algebra 1 or Algebra 2, where we would have learned the idea of a function. Functions aren't really something that we'll deal with in linear algebra. We're only really dealing with transformations, but transformations have the same idea of a function. So let's use what we should already know about functions to kind of understand this idea of a transformation. So in the past with a function, you might have had a function like this. Let's say f of x is equal to x squared. And this f of x notation told you that this was a function f in terms of the variable x. And it tells you that when you plug in some real number value for x, the function f will return to you an output value. So you input an x, f gives you an output based on what you have over here on the right side. So f of x equals x squared, or y equals x squared, is a parabola. So let's pick some values of x and talk about what f of x returns. So if we pick x equals 0, then we're going to get 0 squared, or 0. The value of f of x is 0. If we pick x equals 1, we're going to get 1 squared, or 1. If we pick x equals 2, we get 2 squared, or 4. If we pick x equals 3, we get 3 squared, or 9. And obviously we can see what the pattern is if we continue on. So we're putting in these inputs of x, 0, 1, 2, 3, and the function f is giving us outputs for f of x, 0, 1, 4, and 9. You can think about this like a mapping. Basically, the function f is taking in some value for x and mapping that to x squared. This little arrow here means maps to, or mapping. So x is mapping to x squared. Every x that you put into f will come out as an x squared value, whatever that input was squared. So that's what a function does. And in theory, we could do the same thing with vectors. So let's say I have some vector. We'll just call it the vector x1, x2. So it's a two-dimensional vector. And let's say that if we pop it into some function f, we don't know exactly what f is yet, but if we pop it into some function f, maybe it always comes back out to us as, let's say, negative x1 plus x2, and then 3x1. So if we have a function like this one, where we're mapping vectors from this input to this output, we call this a vector valued function. And you can see here that if we make a table of values for this, we put in inputs, x1, x2, input vectors, and the result that we get out is this vector here, which is f of the vector f of x1, x2. And so if we look at some input-output pairs here, let's say that we input 0, 0. So we input the vector 0, 0. What do we get out? Well, we get negative 0, that's just 0, plus 0. So we get 0 here for the first component. And for the second component, we get 3 times 0, or 0. So that just maps the 0 vector to itself. What if we put in the vector 1, 1? Well, we would get negative 1 plus 1 is 0. And then here we get 3 times 1, or 3. So the function f maps the 1, 1 vector to the vector 0, 3. And then let's say I put in the vector negative 5, 2. If I put that into f, I'm going to get negative 5, or positive 5, plus 2 is 7. So here my output will be 7, and I get 3 times a negative 5, negative 15. So my output is 7, negative 15. So you can really see how we're doing the same thing here, whether we have inputs and outputs of vectors or inputs and outputs of real numbers. It's still a similar kind of mapping. When we do this with real numbers, we call it a function, and that's the most typical language that we use. But when we do this with vectors, we actually like to call it a transformation, not a function. And for that reason, we usually use a capital T to indicate transformation instead of a lowercase f to indicate function. So instead of seeing this function written this way, you'd actually call it a transformation, and you just see it written as the same x1, x2, and then the same output here of negative x1 plus x2, and then 3x1. But we just use that capital T to indicate that it's a transformation, and we usually use the language of transformation and write it with a capital T when we're talking about input-output pairs as vectors instead of input-output pairs as real numbers. Now, when we're talking about transformations, it's important to realize that we're mapping from one space to another. So let's imagine that this is kind of our input over here, and this is sort of our output space over here. So if we were using this to describe the function, this left-hand circle here would be the inputs x, this right-hand circle would be the outputs f of x, or in the case of this transformation here with the vectors, this space on the left is where we have our input pairs x1 and x2, and the right-hand space here is where we have the transformed vectors t of the vector x1, x2. So oftentimes here you'll call this the subset or maybe subspace A, and this the subset or subspace B. So think of A as a set of vectors and B as a set of vectors, and the transformation T is mapping vectors from A into B. We also need to think about the space in which A and B are defined. So maybe A is defined in R3 space, and maybe B is defined in R2 space. In that case, the transformation, it's not only mapping vectors from A onto B, it's mapping from R3 to R2. So we can map across spaces. We can map within spaces too. We can map from R3 to R3 or from R2 to R2, but we can also map across spaces, in this case from R3 to R2 or R2 to R5, or from whichever space to whatever space the transformation is mapping. Now, the vector set A that we're mapping from, this is called the domain of the transformation. The vector set B that we're mapping to is called the codomain. Now, sometimes the domain or the codomain will be an entire space, R2 or R3 or R4, but sometimes the domain or the codomain is going to be a specific subset of vectors within that space. So let's actually say that we have a larger space here and a larger space here. And let's say these blue boxes represent all of R3 and all of R2, and the transformation is mapping from one to the other. So the transformation T is mapping from R3 to R2, like we said here. And let's say that because we've defined circles here inside of R3 and inside of R2, let's say that neither A nor B is all of R3 or all of R2 space, respectively. Let's say that A is a subset of R3, so it's just a specific set of vectors within R3, but not all of the possible vectors that make up R3. And then same thing here, B, the codomain, is a subset of vectors within R2. It's not all of the vectors in R2. If that's the case, then B actually isn't the codomain. In that case, R2 would be the codomain, and B is actually the range. And that's because we distinguish between this idea of range and codomain. So the codomain is the space that's being mapped to, R2 space or R3 space, R4 space, whatever space it is that we're mapping to, that's the codomain. But we may not be mapping to every single vector in the space, and if we're not, then that subset of vectors that are being mapped to within the space is called the range. Those are the vectors that are actually getting mapped to within the codomain. Sometimes these two things are equal because maybe we're mapping to R2, but if every single vector in R2 is being mapped to, then R2 is also the range. So sometimes the space R2 is both the codomain and the range if every vector in R2 is getting mapped to, but if not every vector in R2 is getting mapped to, then R2 is going to be your codomain or whatever space it is you're mapping to, and then the particular set of vectors is the range. So we have the domain, the codomain, and the range. And let's say we even take an example of this. So let's say we have R3 space. We're mapping from R3 to R2, the same transformation we've been talking about. And let's maybe say that every vector in R3 is mapping to something. So we don't have some set of R3. We are mapping literally the entire R3 space. And let's just say we're not even going to talk about which vectors we're dealing with, but let's just say half of the vectors. So we'll kind of cut this in half to signify half of the vectors. But half of the vectors are going to map to, let's say, the 0 vector in R2. So we could kind of signify that here. Let's say this goes here, and all of these vectors, half of the vectors, are going to map to the 0 vector. And then the other half is going to map to the vector, let's say 1, -1. And this isn't any particular kind of transformation, but we're just saying that everything here is going to map to 1, -1. What would be the domain, the codomain, and the range of the transformation? Well, we said that for the domain, we're mapping every single vector in R3, which means the domain is going to be all of R3 space. We know that we're mapping into R2 space, and we can see that with these vectors here, because these are both two-dimensional vectors. So because we're mapping into R2, the codomain is going to be R2. Now, the transformation T specifically shows us that half the vectors in R3 are getting mapped to the 0 vector, and the other half of the vectors are getting mapped to 1, -1. So we're not mapping to every single vector in R2, we're only mapping to those 2 vectors specifically. So the range is not also R2, the range is specifically these 2 vectors, the 0 vector and the vector 1, -1. And you can see how the range and the codomain are different values there. So just remember that we use transformations to map from one vector set to another set. We have to be aware of the spaces we're mapping from and to. Are we mapping from R3 to R2? Are we mapping from R2 to R4? That kind of thing. That the space we're mapping from is the domain, that the space we're mapping to is the codomain, and that the range may or may not be different from the codomain. If we're not mapping to the entire space described by the codomain, but to just particular vectors within the codomain, then we define the range differently than the codomain, and we call out the particular vector or set of vectors that are being mapped to as the range.